Hello everyone, and welcome to Elemental Science Magazine. Today, we'll explore three groundbreaking materials that are already redefining engineering and infrastructure. Metamaterial-based invisibility cloaks, graphene, and self-healing concrete. This session is crafted for professionals who want a technically sound yet accessible deep dive into real-world deployments, enabling science and what's coming next. Let's begin. We're entering a new era where materials aren't passive anymore. They're engineered for control, adaptability, and intelligence. Metamaterials are a class of structured materials that manipulate electromagnetic waves in ways nature never intended. Their defining feature: they bend light, sound, or microwaves around objects, effectively concealing them. In 2006, researchers first guided microwaves around a small metallic cylinder. Since then, the scale has expanded. Now, we see metasurfaces that suppress radar reflection by tens of decibels across wide bands, thinner and lighter than traditional radar coatings. In defense, these coatings are finding real deployment, integrated into stealth aircraft and unmanned platforms. Another domain is thermal camouflage, textiles coated with metamaterial layers that suppress infrared signatures. Military trials have demonstrated meaningful reduction in visibility under thermal imaging. Now, technically speaking, a metamaterial consists of periodic structures, often metallic loops or resonators, smaller than the target wavelength. Each cell interacts with incident waves, generating controlled electromagnetic responses. By designing the geometry and spacing, engineers craft effective values of permittivity and permeability, creating a medium where waves flow around rather than through. Multi-layer metasurfaces or tunable elements, using varactors or MEMS, allow performance across multiple frequencies, bringing dynamic control into stealth systems. However, practical challenges remain. Scaling nanopatterns to meter-scale structures is costly and fabrication-intensive. Many designs only operate within narrow frequency or angular bands. Environmental durability, maintaining adhesion and electromagnetic integrity under heat, shock, or moisture, remains critical. Looking forward, we can expect adaptive metasurfaces on UAVs and naval vessels, smart coatings for sensors, and architectural applications for privacy or camouflage. Metamaterial cloaks are no longer science fiction. They are quietly transforming stealth, defense, and sensing industries today. Graphene is often called the wonder material, a single layer of carbon atoms, perfectly arranged in a hexagonal lattice. It is roughly 200 times stronger than steel, highly conductive both electrically and thermally, and nearly transparent. Let's see how these properties are being applied. In electronics, graphene enables ultra-fast transistors and flexible circuits. Prototype displays using graphene electrodes are already showing improved durability and bendability compared to traditional indium tin oxide. In energy storage, graphene is enhancing battery anodes. By mixing graphene with silicon-carbon composites, engineers have increased charge capacity and extended life cycles, a critical leap for military and electric vehicle batteries. Commercial examples include silicon graphene cells with 15% longer life and faster charging under existing manufacturing lines, showing true industrial readiness. In composite materials, adding small amounts of graphene strengthens concrete, asphalt, and polymers. Infrastructure trials show improved resistance to cracking and freeze-thaw cycles, promising for roads and bridges. In coatings, graphene's impermeability prevents corrosion. Marine coatings using graphene-infused epoxy have extended maintenance cycles for ships and offshore structures. Biomedical devices are another frontier. Graphene's sensitivity allows single-molecule detection, driving new biosensors and neural interfaces, potentially transforming wearable diagnostics and brain-machine technologies. Despite this, three challenges persist: cost-effective mass production without defects, integration, embedding graphene into industrial systems without losing its properties, standardization, defining what counts as graphene quality in products. The future? Over the next decade, graphene-based batteries will enter mainstream EVs and portable devices. Anti-corrosion coatings will become industrial standards. Graphene sensors will move from labs to medical markets. Graphene-reinforced infrastructure will support sustainability goals. In short, graphene's transition from laboratory marvel to industrial workhorse is well underway. Concrete forms the backbone of global infrastructure, but it cracks. Water enters, rebar corrodes, and repair costs mount. Self-healing concrete changes that equation. There are two key approaches: microcapsule-based and bacteria-based systems. In microcapsule systems, healing agents such as epoxy or mineral precursors are encapsulated and mixed into the concrete. When cracks form, they rupture these capsules, releasing the agent that solidifies and bonds the crack faces. In bacteria-based systems, spores and nutrients are embedded in the concrete. When moisture enters, bacteria activate and convert nutrients like calcium lactate into limestone, sealing the crack naturally. Field trials on bridges, tunnels, and pavements show significant performance gains. Cracks up to 0.8 mm heal within weeks, restoring water tightness and extending service life by decades. Benefits include reduced maintenance cycles and costs, improved safety through lower corrosion risk, lower carbon footprint via extended structure lifespan. Challenges include cost, long-term data, and updated construction codes for performance validation. Over the next decade, expect self-healing concrete to dominate high-value projects, tunnels, offshore platforms, and transport hubs, before spreading into mainstream infrastructure. This is the foundation of smart, adaptive civil engineering. If this video helped you see what's beyond steel, share it with your team, comment on the material that excites you most, and subscribe for our next Deep Tech episode on smart materials for aerospace and biomedical systems. Thanks for watching Elemental Science Magazine.